Hello, today we are going to talk about dimensional analysis, but first let's see why we need this. So lots of fluid mechanics problems can be solved using the equations and analytical procedures. However, there are lots of fluid mechanics problems that rely on experimentally obtained data for their solution. And so this is why engineers working on fluid mechanics problems should be familiar with the experimental approaches to these problems so they can interpret the data that comes from the experimental data and to go ahead and have a better understanding on the data, the experimental data. So in this chapter, we consider some techniques and ideas that are important in the planning and execution of the experiments. So first, let's talk about one definition, which is similitude. So similitude is used to measure to the measure of the system, for example, in the laboratory, and then to describe the behavior of other similar systems out of laboratory. So what it means is that, for example, just assume we would like to make a wind turbine, and then and see the effect of the blade size on the performance. So can we make the real blade in different sizes and see if it can improve the turbine efficiency, or how can it improve it? Or do you think uh, how much it would cost, right? And is it safe to do that? Because, for example, if the blade size is going to be very big, and then the system gonna fall down, so it's not safe anymore, right? So what if instead of making real giant wind turbine, which is extremely expensive, we just make a small model, right? Small model. So and test it in the laboratory. So it brings down the cost significantly, and it is safer and also easier to test, right? So, but what if the scale size that we want um, to consider for our small model, let's say that we wanna the small model, if we compare it to the real model, the scale size is gonna be 1/10, right? But then how can we scale down the other variables? For example, the velocity, is it be the same as the velocity of for that real turbine? Or how about the other variables like tower height, or the density, or the viscosity? So can we just say that so everything gonna scale down by 1/10? So the answer is no, we cannot do that. We need to know the relationship between the variables. Then we can say that how much the other variables gonna scale down. So this is why we need this kind of definitions and techniques. So one important thing that I want to recall from chapter 1 is that we say that all equations must be homogeneous in units, right? So we need to consider this fact in this chapter for sure. And now let's go to see what is the what is dimensional analysis, right? Mm. So in dimensional analysis, we show how to develop a meaningful way to perform an experiment. Now, to make a plan for experimental study, we need first to determine what variables can affect on the given problems. So the variables are important. And then when we figure it out what we need for the variables, we need to change one variables at the same time and keep the rest of the variable constant to see the effect of that chosen variable. But we need to have relationship between the variables to see how they affect each other to do to do to see this is how we can relate all of the variables together. So to do so, we need to create dimensionless groups, and dimensionless groups are a collection actually of a number of dimensional combinations of the variables. And now let's talk how we can create these groups. Yeah, I'm also going to solve one question for this chapter, not one, I mean just for the lecture notes, because it is kind of easier to see how, for example, this step that I write down here is going to happen in a real question or real problem. So now let's talk about the how can we create this group. So for creating dimensionless group, we need our PyTerms. We need our PyTerms. So the dimensional analysis is based on the Bachman-Combe Pi theorem. And basically, PyTerm is a dimensionless product. Now, the question is how many of them are required to be created by the given variables in the given problem. So first, we need to consider the number of the basic dimensions that we have. So we can use the MLT system or the FLT system. So it is usually, so we can see that it's MLT. So it's 1, 2, and 3. So our R is going to be 3, right? So it means that R is equal to the number of the reference, the basic dimensions that we have. Now let's consider K, which is the number of the variables. For example, we have, let's say that we know that the diameter of the blade is going to affect our system. We know the, let's say the height of tower gonna affect it. We know the velocity of wind gonna affect the performance of the wind turbine. We know that the rotational speed affect the wind turbine. So let's say we have these four variables that we know that it's gonna affect the problem, right? So now we need to consider the number of them. So one, and let's say pressure is the density and viscosity is also affect our solution, right? So now let's just 1, 2, count them, 3, 4, 5, 6. We have 6 of them. So K is going to be 6. And now the number of pi terms is equal to K minus R. So we know that our K is 6 and then our R is 3. So we can have 3 pi terms. Now let's see if we have a problem, how can we go through it and solve it for this for the dimensional analysis. So first we need to list all of our variables like what I did here and count them. and write it down for k, right? Then express the variables in terms of basic dimensions. So let's say do you want to use MLT or FLT, and either of them they have just three. Yeah, for example, this one has meter, um, length. Sorry, this has mass, length, and time, right? So these are three, and then the next step would be determine the required number of pi terms. That's what I did right here by considering k and r value. Then after that, we need to select the repeating variables for our solution. And the number of repeating variables, it should be equal to the number of the basic dimensions, which in case are, which is our MLT, right? So, but special attention should be given to the selection of the repeating variables in this step, at the step 4, I mean. So, all of the required reference dimensions must be included within the group of the repeating variables. For example, if I need to choose 3 of them as my repeating variables, I need, for example, let's say V, omega, and rho. I need to write down all of the dimension of these three. For example, LT, 1T, and this one is mass L cubic, right? I need to make sure that the combination of them has M, L, and T, right? So, and then we know that they have the all of the required reference dimensions that we consider for the repeating variables, and they have each of the repeating variables has the dimensionally independent of the others. So it means that the dimensions of one of repeating variable cannot be reproduced by some combination of the products of power of the remaining repeating variables. This means that the repeating variables cannot themselves be combined to form a dimensionless product. So let me just write it down here. This is for step 4. So the repeating variable cannot themselves be combined to form a dimensionless group or product. And then now when we consider our repeating variables, we need to form a pi term by creating dimensionless variables. So after that, we need to repeat the previous step for the other variables of the non-repeating variables, right? For example, here, if I say that V, omega, and rho are my repeating variables, I need to do a step 1 to 5 for, let's say, we have D, H, and what else? Mu. But these are the 3 that left, right? So first I need to do all of the steps for this non-repetitive variable, and then next time for for age, and then next time for viscosity. I'm going to show you all of this in the exercises as well. So and then after we create all of the pi terms, we need to check all of the resulting pi terms that we have and make sure that they are dimensionless, right? So this is an important step, because if you don't check it, sometimes you might make a mistake, and then but just simply check it, you know that this is a dimensionless number or not. So and then after that, so I'm not talking about section 7.4 and 7.5 because it just gives some more information about dimensional analysis. I'm going to show all of them in the example. So, and then we have, there are some common groups of dimensionless group in fluid mechanics, that we can use them in some particular questions. And also we can also interpret them physically. And for example, here for the Froude number, right, we can say that the ratio is because of the inertial force and then the gravitational force, right? So this is how we kind of interpret it. So inertial force over the gravity, and then and also we can just demonstrate it by considering a fluid particle moving along a streamline. So, but one of the most important of this dimensional group is the Reynolds number. So, which is the inertial force over the viscous force. This is one of the important of the formula that we're going to use it in the, I think, next chapter. So rho VL over mu. And now let's talk about the correlation of experimental data. So when we create pi terms, we need to use them, right? To interpret our data, we need to kind of need to find a relationship between pi terms. So if we have only one pi term, so one thing that I think I forgot to tell you, yeah, about the expression of the pi terms. So for example, if we find, if we have in this particular example that I tell you, we have r as 3 and we have k as 6 and k minus r is 6. So means that we are going to have 3 pi terms, right? So then how can we express them and find a final form of a relationship among our pi terms? So we're gonna have pi term equal to pi 2 and pi 3 in this question, right? So be careful also about that. And now when we want to, when we created the pi terms and trying to see the relationship between pi terms, if we have only one pi term, so it is pretty easy, and we can just say that pi 1 is equal to c and where c is a constant. Or if we have two pi terms, right? So we are going to say that the pi 1 is equal to is a function of pi 2, right? And we can, because it's just two pi terms, so it can very easy to just show it in a simple graph. But if the number of pi terms increase, then it's going to be really difficult to display the result in the graphical in graphic and in just kind of interpret them. So let's see what else we have. So now we are going to talk about the modeling and similitude. So for doing that, let's see. This is how can we. So we talk about this because then this is how can we are going to use our PyTerms. So now there are two definitions that we are going to see in this chapter a lot. The first one is a model and the other one is a prototype. So the model is a representative of a physical system, and that is, used to predict the behavior of the system that we are trying to find some other effect or on it. And then a prototype is the physical system. So now let's just assume that we have a prototype, which is our physical system, and a model that is used to predict the behavior of the system, right? So let's go back to our wind turbine problem. So in the wind turbine problem, the model that we have is the small model that we have in the laboratory, and then the real turbine that we have is going to be considered a prototype. Now, what it means by them is that, for example, all of the PyTerms that we find for that particular problems, they are all must be equated between the model and prototype. So let's write down, for example, I found pi1 equal to Reynolds number, for example, rho v d over nu, right? So, and then over mu, sorry. And then let's say I have the values of, for example, the large turbine, which is our prototype, and then we have our small turbine, right? So let's say that we know the density of both, and we know the viscosity of both, and we know that, let's say, the diameter of the first one, let's say it's 10 meter, and then the diameter of the second one is going to be 1 meter, right? And now, and if we know the velocity of this one, let's say 5 meter per second, we are trying to find out the velocity of the small wind turbine, the velocity of wind that we need to apply for that model in the laboratory. So this is why we need to know the relationship between the PyTerms. And so this is how we are going to say that then pi1, for example, in just this particular question of the prototype equal to pi1 of the model. What it means is that, for example, we know that all of the variables for the prototype, so I'm going to write it down, and we don't need to consider p in this, but I just wanted to write it down, right? And then we also need to consider all of these variables for the model, and d of the model, and then of the model, right? And now, because we know all of the things here, right, and we can calculate the diameter, and we know density and viscosity, so we can easily find out the velocity. And now this is how we connected the PyTerms together. And let me just highlight these two finishing here. And I'm going to solve one question of it in the next video.